Hello, geometry students. We are back for another lesson, and today we are going to be covering Chapter 4, Lesson 2, and we're going to be talking about reflections. So yesterday we were talking about transformations, and this lesson is going to be talking about reflections. So a reflection, another word that a lot of times we use is a flip. So it is a transformation across a line. This is known as the line of reflection. So sometimes we're reflecting across the x-axis, the y-axis, or y equals x, or x equals 3. So you're always reflecting across a line of some sort. All right, so does this transformation appear to be a reflection? So is there a line that we can reflect this across? Is there a line that this reflects across? And the first one is yes, it does appear to be flipped across the line, and letter B, it's not. This would be a slide, what we were doing in lesson 4-1. All right, so when we're going to do this reflection across this line, every time we do this, we're going to take this point, and I like to draw it so that it comes down perpendicular. And then however long this is, I'm going to go that same distance over here. So you do that with every point until you get your new figure. Okay, and this is what they get. So you can see that this distance right here is perpendicular, and this distance is equal to that distance, and you do that with all 4 points. Okay, so that is called your line of reflection, and each point, so pre-image A to image A prime, is the same distance across this line, and remember, it has to be perpendicular. All right, rigid motion. Remember, we talked about this yesterday. If we were talking about a rigid motion, that does not change the shape or the size. So if I start with the triangle, I am going to end up with the same size triangle. Okay, it's not going to be a different size. It's not going to change into a quadrilateral. It will stay the same shape and the size. So is a reflection considered an isometry? So if we reflect across a line, does it stay the same shape? Does it stay the same size? And the answer is yes. A reflection is a rigid motion. All right, before we actually do this problem, I'm just going to talk about a couple different points here. So let's start with this point 2, 3, just a point right here. And I'm going to reflect across the x-axis. Okay, so I'm going to change this every time. So we're going to try to figure out some rules here. So when we reflect across the x-axis, what happens? Well, here's our x-axis right here. And we said it always has to be perpendicular and then the same distance. So if it went from here, 1, 2, 3, then we're going to go down 1, 2, 3. So what does this new point become? So it was, the pre-image is 2, 3. What does it become when we go across the x-axis? Well, it still stays x. And now what happens to the y is it becomes negative. So would that happen for every single point? So if I pick this point right here, which is at -2, +1, when I reflect across the x-axis, it goes to here. So I'm still at -2, but now instead of being at a +1, it goes to a -1. So when we reflect across the x-axis, what happens? Does x stay the same, and do we change the sign of the y value? Okay, all right, now let's try reflecting. How about I just change colors here? If I reflect across the x-axis, so now I'm going to reflect a point across this x-axis here. So let's just stay with the same point, 2, 3. And the same thing happens. So I go 1, 2 units. So I have to go 1, 2 units. So now what is this ordered pair? And when I go across that y-axis, what happens? This becomes a -2, and this stays 3. So what happened? When I went across the x-axis, did the x stay the same? And now when I'm going across the y-axis, what's happening to my y values? Is my y value staying the same? So now is it the opposite of x and y stays the same? Okay, another very common line that we go across is y equals x. Well, y equals x is this line that comes right here, right dead smack down the middle. So if we take a point over here, let's just take, it doesn't really matter which point, let's just take that point right there. So what is that point right there? It is -1, +2. So now when I go across that y-axis, this line, y equals x, what is that new point? Now remember, it needs to be perpendicular. So if this slope is 1, the other slope has to be a -1. Okay, so it has to be coming down perpendicular. So which point are we going to be at that point? Is it going to be this one right here, which is going to be at a 2, -1? So what happens when we reflect across y equals x? What happened to those numbers? And did they just switch? So does it go from becoming x comma y? Does it become y comma x? All right, so those are 3 of our lines. What do you think is going to happen when we reflect across the line that's going the opposite way here as x? So if we do it the other way, instead of going this positive direction, if I come this negative direction, how do you think that is going to affect it? So instead of the ordered pair being x comma y, if we reflect across the axis y equals -x, now what happens to those? So what do you think is going to happen to those ordered pairs? So if it's 3, 1, what do you think it is going to be when it switches? All right, hopefully you guessed this. So this is what we said. When it's the x-axis, I wrote it with x's and y's. So I said x stays the same and we get the opposite of y. When we reflect over the y-axis, I said y stays the same and we get the opposite of x. When we reflect over the y equals x, so when it was going like this, I said that they switched spots so that it was y comma x. So I used x's and y's and they're using a's and b's. So when it reflected over the axis that goes the other way, whoops, what happened to my screen here? When it comes going the other way, this way, they switch places so it becomes -y comma -x. Okay? All right, let's go back and do this problem. Oops, it didn't go where I wanted it to. So when we do this problem right here, oh, we're still not on the right one. I think they're switching orders on me. I'm not sure what's going on. Okay, so when we do this problem here, we'll do just the first one. We're going to reflect over x equals 3. So when we have x equals 3, this becomes 1, 2, 3 is this line right here that we're going to reflect over. So when we take this point, 1, 3, okay, that's where A is. In order to find out where that prime is going to be, so here's your pre-image, and we're going to go to the image, it's, if we are going to go 1, 2, so I'm going to go 1, 2, so here is where A prime is going to be. So A prime is going to be at 5, 3. And now I do that same thing for every single point. So if I have B is at 5, 2, here's where B is. Then I'm going to go, if I'm going over this axis, I go 1, 2, 1, 2. So B prime ends up being at 1, 2. And now if I pick C, C is at 2, 1. Here's C. C prime is going to be over here. So C prime is going to be at 4, 1. Okay, so if I connect all of these primes, 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 this is what we become when we reflect over that x-axis. So remember, it always has to be perpendicular and you go the same distance on each side. All right, so what are the coordinates of the image of GH, where G is -3, 4 and H is 2, 1 after reflection over y equals x? Well, I like to just go back to my rules. And in the rules, when we're reflecting over y equals x, that's when it goes to -y, -x. So G, they're going to switch places, and this is going to become a -4. And this is going to become a +3. So G prime and H prime. So I'm going to switch them and switch their sign. So it becomes -1, -2. So I like to use the rules. Of course, you can certainly, if you want to graph it, if that works better, you can certainly do that too. All right. Oh, here's the graph of them doing that and where they go. So a composition of transformations is going to be one or more transformations. Okay, one followed by another. I'm not quite sure why that was there. Okay, one transformation followed by another. So a glide reflection is a translation plus a reflection. So we translate and then we reflect over. So it's two things, glide and then a translation over. That's called when a figure can be mapped onto itself by a reflection over a line. That is called your line of symmetry. So when we go back here, this could be called our, this is our line of reflection. My apologies. This is your line of reflection. This line of symmetry is when you're in one figure. Can I take and fold it over that line? And does it fold on top of itself? And if I fold it here, does it fold on top of itself? So it has two lines of symmetry. When we reflect over a line, that's when it's the line of reflection. So how many does the hexagon have? And how many does this last figure have? All right, so the hexagon has one from the middle of every side and from angle to angle. So there's a total of 1, 2, 3, 4, 5, 6 of those, and only one for that last figure. All right, lines of reflection in a regular polygon. Remember, what makes it regular is that all the angles are the same and all the sides are the same. That's what's going to make it regular. And it matches the number of vertices. So in a triangle, there's 3 vertices, 3 lines of reflection, if it's an equilateral triangle. In a square, 4 vertices, there's 4 lines of reflection, as long as it's a regular figure. So regular pentagon, all the angles are the same, all the side lengths are the same, there's going to be 5 lines of symmetry. So that only works for your regular polygons. All right, looks like we're at the end of the lesson and ready for your homework. So good luck.